What specific problem does the vec-to-vec method aim to solve in the context of text embeddings, and how does it relate to existing methods for representation alignment?
The vec-to-vec method aims to solve the problem of unsupervised translation of text embeddings between different models, without requiring paired data or knowledge of the original encoder. This is particularly challenging because existing methods for representation alignment typically assume the availability of corresponding embeddings from different encoders, which is unrealistic in many practical scenarios. Vec-to-vec builds on concepts from previous research in unsupervised embedding translation and representation alignment, such as cycle consistency and adversarial losses, but distinguishes itself by successfully translating embeddings from one model's space to another's, achieving high cosine similarity and accuracy metrics. Unlike traditional alignment methods that rely on known correspondences, vec-to-vec learns a universal latent space that captures the geometric structure of embeddings, enabling effective translation and information extraction. This innovative approach demonstrates that it is possible to harness the commonalities in representation spaces of different models, thereby advancing the field of text embeddings significantly.
How does the proposed vec-to-vec method work? Please illustrate the process step by step, including the roles of input and output adapters, backbone network, and the training procedure.
The proposed vec-to-vec method operates through a modular architecture designed to translate embeddings from one model space to another without paired data. First, input adapters, A_1 and A_2, transform embeddings from their respective encoder-specific spaces into a shared latent representation of dimension, Z. Next, these adapted embeddings are processed by a shared backbone network, T, which extracts a common latent embedding. The output adapters, B_1 and B_2, then translate this common latent representation back into the original embedding spaces of the two models. During training, the method employs adversarial losses, cycle consistency, and vector space preservation to ensure that the generated embeddings closely match the original embeddings in terms of both geometry and semantics, ultimately allowing for effective unsupervised translation.
Can you provide a concrete example of how the vec-to-vec method translates embeddings from one model to another? Walk through an example with specific embeddings and describe the transformations involved.
The vec-to-vec method translates embeddings by first encoding them into a shared, latent space using input adapters specific to each model. For instance, consider embeddings U_I equals M_1D_I, generated by an unknown encoder, M_1, and embeddings V_I equals M_2D_I, from a known encoder, M_2. The input adapter, A_1, transforms U_I into a latent representation, while A_2 does the same for V_I. The shared backbone network, T, then extracts a common latent embedding from these adapted inputs. Finally, the output adapter, B_2, translates this latent representation back into the embedding space of M_2, resulting in a translated embedding that closely aligns with V_I, achieving high cosine similarity scores, as demonstrated by the method's performance metrics, such as a cosine similarity of up to 0.92.
What theoretical advantages does the vec-to-vec method offer over previous methods for embedding translation, especially regarding the preservation of semantics and geometry of embeddings?
The vec-to-vec method offers significant theoretical advantages over previous methods for embedding translation by enabling unsupervised translation without the need for paired data, which is a common requirement in earlier approaches. It achieves this by leveraging the strong Platonic representation hypothesis, positing that different neural networks trained on similar objectives converge to a universal latent space. This allows vec-to-vec to learn a shared latent representation that preserves both the geometry and semantics of embeddings, ensuring that translated embeddings maintain their relative relationships and semantic meanings. Specifically, vec-to-vec employs cycle consistency and adversarial losses to ensure that embeddings can be accurately translated back and forth between spaces, thus preserving their original structure. As a result, it demonstrates high cosine similarity scores and effective attribute inference, indicating that the semantic content of the embeddings is retained throughout the translation process.
How was the effectiveness of the vec-to-vec method validated in the experiments? Discuss the datasets used, experimental design, and the metrics for evaluating performance.
The effectiveness of the vec-to-vec method was validated through a series of experiments using diverse datasets, including the Natural Questions (NQ) dataset for training and evaluation, as well as TweetTopic, Mimic3, and the Enron email corpus for information extraction tasks. The experimental design involved training 36 distinct vec-to-vec models on 1 million embeddings from NQ, with evaluations conducted on various embedding pairs to assess translation quality. Performance was measured using 3 key metrics: mean cosine similarity, TOP1 accuracy, and mean rank, which quantified how closely the translated embeddings matched their target embeddings. Results showed that vec-to-vec achieved cosine similarity scores as high as 0.92 and TOP1 accuracies up to 100%, demonstrating its superior performance compared to naive baselines and Oracle-aided optimal assignments. Additionally, the method's ability to perform zero-shot attribute inference and inversion further validated its effectiveness in preserving semantic information during translation.
What limitations or challenges might the vec-to-vec method face when applied in real-world scenarios, particularly concerning generalization to different domains or embedding models?
The vec-to-vec method, while promising, may face several limitations in real-world applications. One challenge is its reliance on the assumption that different embedding models share a universal latent structure, which may not hold true across all domains or embedding architectures, particularly those that are significantly different from the training data. Although the method has shown high cosine similarity and accuracy in cross-backbone pairings, the performance may degrade when applied to embeddings from highly specialized or out-of-distribution domains, as indicated by the varying results on datasets like medical records and tweets. Additionally, the method's effectiveness in preserving semantics during translation could be compromised if the embeddings contain domain-specific jargon or unique contextual nuances not represented in the training data. Finally, the need for substantial amounts of training data to achieve optimal translation performance suggests that in scenarios with limited data, the method may struggle to generalize effectively.